Okay, welcome to section 2 of chapter 10 of your text. This is entitled Bronsted Lowry acids and bases. This expands the meaning of acid and base to um, something. Well, historically, here's the situation. Historically, Arrhenius came up with his uh, acid and base theory. He was active in the 1890s, early 19 aughts, early 20th century. And I did mention in class, I'll say it again, he was actually the first one to analyze the effect of carbon dioxide on, on average temperatures. And he actually published the first paper, and he didn't publish the first paper on the effect of trace gases in climate, but he was the one who calculated, the first one that predicted 2 degrees Celsius increase on doubling carbon dioxide levels. This was in 1896. And so this really isn't the global warming, climate change, whatever you want to call it. Um, it's not a new concept by any stretch. It's been around for, well, 1896, do the math. That's what, 125 years. I think, is that 100? I think it's 125 years. That sounds right. So it's been around for a while. But that was Arrhenius. He was a physicist. He got a Nobel Prize. He actually won a Nobel Prize in chemistry, and he makes jokes about it that the Nobel Committee made him a chemist. But anyway, he was a bright guy, and a lot of the stuff talking about, we're talking about in this course, at least in the inorganic part and in this part, is influenced by him. Now, Bronsted and Lowry acids and bases, add this as something. Arrhenius bases are kind of limited. It's hydrogen, sulfuric acid. Okay, it goes, it puts it in water, it ionizes, it gives off hydrogen ions, and a base was hydroxide, or sodium hydroxide. You dissolve in water, gives sodium ions and hydroxide ions. Well, that is a little bit limited. So Bronsted and Lowry, I don't have any historical trivia on them, at least not on the tip of my tongue, where an acid is a substance that donates hydrogen ion. That sounds a lot like Arrhenius, Arrhenius. And a base is something that accepts hydrogen ion. Now that's a little different. And when we look at this, you're going to see that the acid is a substance that donates hydrogen ion. That's a little different than the Arrhenius definition of an acid too. Arrhenius it produces hydrogen ion. Okay, well, it's a fact that hydrogen ion, H plus, really doesn't exist in solution. It's going to be attached to something. And you remember you did all these, you looked at these formulas with the, a few chapters back on non-bonded electrons. H2O2, it has 2 unshared electron pairs, NH3 has 1. Well, you have a hydrogen ion around, it's going to find one of those. Okay, it's going to find one, and in water, it's usually going to be water. So you see what happens there. You have a hydrogen ion reacting with water to give you a hydronium ion. That is, and even that's a simplification, but that hydronium ion, that is how you will find hydrogen ion in water. Okay, if you put an acid in water, acetic acid, hydrochloric acid, sulfuric acid, it's going to ionize, it's going to give you hydrogen ion, and that hydrogen ion is going to look for water molecules to form hydronium ion with. Okay, we say the sulfuric acid is donating hydrogen ions to water. And you see there in the hydrogen chloride in water. Hydrogen chloride donates a hydrogen ion to water to give you hydronium ion and chloride. But now what? Now look, water is now acting as a base. A base is a substance that accepts H+. Well, water accepted H+ from the hydrogen chloride to give you hydronium ion. Okay, so water can act as a base. So you see right here, we've expanded the definition of bases. where water's a base. We can go on. And this is about water. But, well, this is Bronsted Lowry, but with ammonia and water. Ammonia is a Bronsted Lowry base. It can accept a proton. And remember, if you have the, let me go to the whiteboard, and hopefully the whiteboard is working this time. We'll see what we have here. Okay, you take ammonia. Remember the structure of ammonia, NH3. You've got this lone pair of electrons. Okay. Oh no. Scared me for a second there. You got this lone pair of electrons, and in the presence of water, where water acted as a base last time, well, ammonia wants these protons a little more than the oxygen does. See, remember, oxygen is more electronegative than nitrogen. So oxygen wants the electrons. It'll take protons if it absolutely positively has to. But if you've got if you've got water and you've got ammonia together, and well, here we've got these protons that we need to donate to somewhere. Well, nitrogen is going to have a lot more inclination to take them. So you're going to take these, they're going to react, and you're going to get which you should recognize as ammonium ion. And hydroxide. Let's put all the electrons around there. So you've produced hydroxide ion. And you'd call it the compound ammonium hydroxide. And sometimes when you buy household ammonia, I think every once in a while you might see ammonium hydroxide on a label, but it's mostly just a solution of ammonia and water. There's a little bit of that hydroxide in there because ammonia is actually a fairly weak base. But you see, that's the type of reaction that's going on. Oops, so this is what's going on here. So you have the ammonia is the base, water's the acid, and a base is a proton or hydrogen ion acceptor. Acid's a proton or hydrogen ion donor. You will find, if you're around enough chemists, that they will talk about hydrogen ion as a proton. If you think of what a hydrogen atom is, it's a proton, a nucleus, and it's an electron. A hydrogen ion is just a proton, and it's you'll see a lot of that. We say things like a proton acceptor, not a hydrogen ion acceptor, and even with the hydronium ion, we'll abbreviate that just H plus. But I'm going to try to stay strict with the terminology as much as possible. But if I say a proton, in context of acids and bases, you know what I'm talking about. All right, so you've got a base, you've got an acid. There's a transfer of an electron. The process, the acidity, the concept of acidity is based on the transfer of a hydrogen ion or hydrogen ions. So if you do this, you'll get a basic solution because there's hydroxide in there. And we have, going back to the acids, you notice in this one here, you put hydrogen chloride in water, and then you're going to get an acidic solution. Okay, so it's always going to be the case in water that a basic solution is going to contain hydroxide ions, and more hydroxide ions than hydronium ions or hydrogen ions, and an acid is going to contain more hydrogen ions than it's going to contain hydroxide ions. And we're going to be talking about that. We'll be talking about that near the end of this chapter. So they ask you to, in the following reactions, identify the Bronsted-Lowry acid and base and the reactants. Okay, well, this should be an easy one for you. I'd hope so, because those compounds there, you should you should recognize as nitric acid. B, you should be able to figure out that could be called hydrofluoric acid, and it's reacting simply with water. So you're only identifying the acid and base and the reactants. So right there, you see what happens to the nitrate, the nitric acid. It gives up a proton to water, and it leaves nitrate behind. So right there, you see nitric acid, well, hydrogen, HNO3 is the acid, and it's transferring, it's donating a proton or a hydrogen ion. What's accepting it? The Bronsted-Lowry base is a hydrogen ion acceptor. So it has to be water, because water is taking on a hydrogen ion and giving you hydronium ion, H3O+. Or sometimes you call that hydrogen ion, but hydronium ion is a little more accurate. And the same with the hydrogen fluoride and so forth. So you see what's going on there. It's an acid-base reaction. Now we extend this to something called conjugate acid-base pairs. Acid-base reactions are reversible. In a solution like this, where you have HA, it could be any acid, and a B, which could be, could be water or some other base, you're going to have an equilibrium between both sides of the reaction. It's very rare that a chemical reaction is equal on both sides, that you have equal amounts of things on both sides. But in any case, this type of process, you're going to have the reverse reaction going on. It's just, okay, if you have a strong acid and water, you're going to have like hydrogen ion, like you put HCl into water, you're going to have hydrogen ion, H3O+. You're going to have the hydronium ion plus chloride. It's going to be overwhelmingly in that direction. But there's a very, very tiny amount, real small. They say these things are completely ionized. Well, yeah, they are. And but every now and then you're going to have a hydronium ion is going to give up a proton to chloride ion, and you're going to have an HCl molecule there for a little bit until it finds another water molecule to do that exchange with. So that means that there's protons being transferred back and forth all the time. So not only is the reactants acids, not only are the reactants an acid and a base, but the products are as well. And that gives rise to a concept that we call conjugate acids and bases, conjugate acid-base pairs. For every acid, Bronsted-Lowry acid, for every Bronsted-Lowry acid, a proton donor, there is a corresponding conjugate base. And for every proton acceptor, that is a Lowry-Bronsted base, there is a corresponding conjugate acid. And you have to learn, you have to be able to learn to pick those out. Now, look at that equation on the slide there. You'll see that the only thing that really happens in this reaction is that an electron is transferred, a hydrogen ion is transferred from this generic acid, HA, to this generic H, B, to give you a generic conjugate base, A-, and a generic conjugate acid, BH+. That reaction can reverse. We typically say, what's the reactants? The left-hand side of the reaction, that's the acid and base. The conjugate acid and conjugate base are on the other side, are going to be the products. a conjugate base, a conjugate or an acid and a conjugate base, or a base and a conjugate acid are going to be related only by the transfer of a proton. So when you look at a chemical reaction, they ask you, what's the acid and what are conjugate acid base pairs? You look for some, could be an anion, I mean, some piece of a molecule that shows up on both sides of the equation and is related, where they're both related, where the only difference between them is the transfer of a proton. All right, so we'll, and there's going to be always going to be two conjugate acid base pairs in a Bronsted-Lowry acid base reaction. And you see each pair is related by a loss or gain of a hydrogen ion. And we'll see something here. If you have, they use ammonia here, ammonia and water. One conjugate acid base pair is NH3, and the other is NH4 plus. The other, and that's one of them. The other one is H2O, which is the acid. It's the acid base pair is water and hydroxide ion. You have here, you see, everything on both sides has hydrogen in it. So this is a good example to point out what I'm saying. What's the conjugate acid base pair? Well, one has to be on the reactant side, the other has to be on the product side. Okay, so ammonia. You have two species that are related, that are involved in the reaction, but which of the two, ammonium ion or hydroxide ion, is related to the ammonia by only one hydrogen ion? And you see, it's going to be the ammonium ion, because it's certainly not hydroxide. The ammonia does get a proton from water to give hydroxide ion, but there's more of a difference. The only difference between ammonia and ammonium ion is that it's one hydrogen ion. That's it. And the same thing with water. You look at water, it has lost one of its hydrogens as a hydrogen ion to go to hydroxide. Okay. So let's write the conjugate base for each of the following acids. Let me go to the whiteboard. Let's see, HBr, H2S, and H2CO3. Okay, it's wait a minute. I think it was HBr, I think, H2S, and H2CO3. All right. Where are we here? HBr, H2S, H2CO3. Okay. Okay, we're back here. Okay, I had those right. Okay, done inking. No, I did that again. All right, we want the conjugate base. Okay, well, what here is going to be, okay, this hydrogen ion goes somewhere, right? It's got to go somewhere. It's going to be related by a single hydrogen transfer. And what's you have to, it's got to be a negative ion, right? Okay, so it's got to be bromide. H2S. Well, I got H plus. Okay. They say, what's the conjugate base of hydrogen sulfide? Well, the conjugate base has to be something that is one proton or one hydrogen ion less than hydrogen sulfide, so it's going to be HS minus. Or is it SH minus? We'll see. I confuse these. When you work with this stuff a lot, sometimes when you work with things a lot, you get better at keeping them straight, and other times when you work with them a lot, you just are so used to writing them down, you just write them down in any order. But then anyway, here, what's one proton less or one hydrogen ion less than this carbonic acid? Well, it's going to be, okay, well, this is going to be your conjugate base. This is going to be your conjugate base. And your conjugate acid, or your conjugate base here, is going to be the bicarbonate ion. Okay, so it's going to be that one. Okay, so and you're going to see that on the slides. You're going to see that on the slides as well. So what we have here, and they've got well, they've got another one where write the conjugate acid, but we'll get to that. So you see the HS minus. Okay, they put the HS minus. SH, written SH, that's also a very common. In fact, you're actually going to see these, and I think it's the next. I think it's the next. I think it's the next module. Yeah, it's going to be the next module. You're going to see SH that's a functional group. An organic compound is a sulfhydryl group or thiol group. So that's another reason that I mix these up sometimes. Okay, but that's you see the conjugate bases there. Now, conjugate acids for each of the following bases. Remember, we're talking Bronsted Lowry, so it does not have to be hydroxide. So you've got nitrite, you've got ammonia, and you've got hydroxide ion. Well, let's go ahead and clear this out. You've got nitrite. Oops. You've got, I think it was ammonia, and hydroxide. What's a conjugate acid conjugate base pair? It's two species that are related by only a hydrogen ion transfer. So something's got to, they tell you these are bases because they're asking you for the conjugate acid. So in all of these cases, you're going to add a proton to them, or hydrogen ion, and you're going to get, well, HNO2, ammonium ion, and water. Okay, so water is the conjugate acid of hydroxide ion. And you can think of the hydrogen ion as the conjugate acid of water. Or as well, it's an acid, and water is the base there. But you know, hydrogen, actually in this case, water is both a, let's see, is it both a conjugate acid and conjugate base in this case? Or something like that. Yeah, it's definitely the conjugate acid. Well, it's, well, this is the base, this is the acid, so this has got to be both. Water is particularly interesting because it can act as both an acid and a base. So that's something to keep in mind. It's called amphoteric, and they do use that term somewhere in the text. Okay, so you do that, and there's those. You see how those work. Okay, this is one of the slides I had to fix. Okay, so now here's another learning check. Identify the sets that contain acid-base conjugate pairs. Remember, only a single hydrogen ion exchange. That's it. Okay, so you're going to have some things. You're going to have something that's going to be they're going to be related only by a single hydrogen exchange. Okay, look at number one. Well, HNO2 to NO2 minus. Well, that's going to be definitely That's going to be definitely one. What about H2CO3 and carbonic acid and carbonate? Well, that's two, right? I mean, that's actually two changes. So really the conjugate acid and conjugate base, uh, carbonate really is not the conjugate base of carbonic acid because it's just a single proton transfer. Okay, so that's not a conjugate acid base pair. If you had, okay, let's go to the whiteboard again. If it went this way, if it was H2CO3 to H plus HCO3 minus. Now that is a conjugate. This is a conjugate acid and this is a conjugate base. But just remember, it's just one proton transfer. That's the key there. Okay, and then obviously number 3 can't be because that's not related by only a hydrogen transfer. It's also related by the chloride being becoming bound with 4 oxygen atoms. So that is not conjugate acid, conjugate base. It's that's not an acid base conjugate pair. This one we've already looked at that, and yes, it's going to be because there's only one hydrogen ion are being transferred. Well, you have HS minus, that's negative, and that might be another key to a tip off that, well, maybe this thing's maybe this is a base, and you add one proton to it or one hydrogen ion to it, then you're going to get hydrogen sulfide. And then again, ammonia and ammonium ion are going to be a conjugate acid base pair, or well, in this case, ammonia being the base. And you see, there's pretty much, as I said, there's the first one is an acid and a conjugate base. Then the next two are not acid base pairs, and then the other two are a base and conjugate acid pair. What do we have here? Identify the conjugate acid base pairs in the following reaction. Well, this should be easy. I mean, HNO3, that's nitric acid, so that's obviously going to be the acid there. And ammonia, that to be a Lewis base. So you have the acid and the base there. Now you got to just identify what the conjugate base and acid are. Well, a nitrate is related to nitric acid by only a proton transfer, and ammonia is related to ammonium only by a proton transfer. So you're going to have the acid conjugate base are going to be nitric acid and nitric acid, or nitric acid and nitrate. The ammonia is a base, of the base conjugate acid pair is going to be ammonia and ammonium ion. And you see they give you the steps on doing this. It's a kind of longer way of explaining all this stuff. But in the reaction, what's the proton donor? What's the hydrogen ion donor? I keep saying proton. What's the hydrogen ion donor? Okay, it's nitric acid, and it donates it to ammonia. Nitric acid is the acid, and nitrate is its conjugate base. And then similarly for ammonia, where NH3, I missed that one. It should be NH subscript 3. That gains a hydrogen ion to form NH4 plus. Thus, NH3 is the base, and NH4 plus is its conjugate acid. All right. So the conjugate acid base pairs, they tell you to write them. Where nitric acid, nit is nitrate, That's the acid and its conjugate base, and then the other is the base and its conjugate acids. It's convention where the reactants are the acid and base, and the products are the conjugate acid and conjugate base. So that's it for section 2. We'll see you again on